Good afternoon. I'm Gurban, candidate of Master's degree in Mechanical Design and Robot Engineering Department, supervised by Professor Kim Jong-il. Today I will present my graduate degree thesis research. My thesis research is a study on teleoperation of mobile manipulator based on virtual reality. This presentation is divided through 7 parts as listed here. First, I want to introduce my work. I developed this compliant mobile manipulator with remote teleoperation system. This mobile manipulator is only 2.2 kilograms, which makes it possible to attach a quadrupedal robot. As you can watch in this demonstration, user can perform complex and delicate tasks. One of the distinct features of this manipulator is a torque control ability, which makes it possible for being compliantly controlled. I attach depth sensor camera on top of the gripper and in front of the quadrupedal robot for remotely visualizing outside environment using virtual reality headset. I also developed virtual reality application for remotely control the robot and inspect robot's virtual reality real-time state. I demonstrate performing several tasks to show the capabilities and overall usability of the system. One of the distinct features of this system is a remote control station is also mobile, which is different than prior work done by other researchers. I mostly focused on users' comfort, such as ease of use and reducing bad effects such as nausea and motion sickness. Then I will present a review of related literature. Manipulators have been developed mainly for replacing hard and repetitive task labor from human in factories and becoming one of the most well-established part of the industry. Since recent years, manipulators are becoming lighter and cheaper to manufacture, which enables researchers to focus on mobile manipulator, collaborative robotic arms.
Could you please use red button? You can use. Actually, I don't know which part you are reading. So you can use this. So you have to point which part you are reading. Okay.
From beginning, mobile manipulators are developed for being used in industrial atmosphere, being inside factories, replacing hard labor work. But since recent years, mobile manipulators are becoming trend in this field because actuators are becoming cheaper and easier to manufacture. There are distinct differences between industrial robotic arm and mobile robotic arm. Industrial robotic arm has to be robust, strong, and accurate for performing tasks. But mobile manipulators arms are, on the other hand, is totally different. It has to be used in use cases of performing dynamic tasks in unstructured environment. It has to be most of the time these manipulators and leg manipulators are going to be alongside with a human. For this reason, it has to be collaborative and safe. From my perspective, virtual reality is one of the most fascinating things created by humans. Thanks to the recent advancements in this field, portable headset devices became available for general purpose and for general people. These devices mainly developed for entertainment and game industry, but 6 degrees of freedom capable tracking capabilities makes it perfect use for controlling robots as well. Since beginning, handheld controllers are go-to option for controlling programming industrial arms. These handheld controllers are always used by professionals, since industrial robotic arms are not reprogrammed too often. For this reason, developers are focused on other features such as tuning accuracy. On the other hand, HMD with floating joystick controllers are total opposite and lack of industry level accuracy. But these systems have other distinct features such as being intuitive, rapid, and fast, even when performing the most complex tasks, which makes it perfect using this human in-loop system, as it's shown in this video. Today, many robotics research laboratories, startups, companies utilize this technology for leveraging their robot capabilities and advancements. Researchers from Italy collaborate for creating universal teleexistence and teleoperating system. Previously, in IIT University, researchers developed hydraulic quadrupedal robot, and now they also developing mobile manipulator to attach and force feedback control sensing teleoperating device. Also, they utilize a digital twin for visualizing in virtual reality application built in Unity. This system has many worth mentioning features, but they lack of comfort for the user. For example, the remote teleoperating device are fixed and not mobile, while robots are mobile. Nowadays, many companies started selling their robots with teleoperation capabilities, such as Poland Robotics company from France. Richie is a humanoid robot teleoperated with virtual reality headset. Extent Robotics startup is selling software package for remotely teleoperating industrial robotic arms using virtual reality headset. Extent Robotics company insists and proved that by using virtual reality, non-expert users can utilize most out of the robot. They demonstrate in many occasions easily performing complex tasks, delicate tasks, such as filling up cup beer in this video. Jeffrey et al. From MIT University published this paper with the title of Baxter's homunculus. This homunculus model, user feels like controlling the robot from inside. This model's distinct feature is reducing nausea and motion sickness, which is the most important, because this problem is one of the biggest and hard to overcome in overall virtual reality headset systems. Finally, here is the state of art. This teleoperation system developed by Team Nimbro. Nimbro is a robot competition team of the Autonomous Intelligence Systems Laboratory from University of Bonn, Germany. Less than 2 months ago, this team received $5 million prize from ANA Avatar X Prize Grand Challenge. And my system have many similar cases with this system. My research objective is to develop a patrol robot with real-time teleoperating system. I divided this task to 4 smaller tasks. The first one is to build intuitive and user-friendly graphical user interface application with a target device of Oculus Quest 2. Second is to build a real-time control system for manipulating and high-level communication between the system and graphical user interface application. The third is to design and build a lightweight robotic arm and gripper. Last but not least, integrating this manipulator with quadrupedal robot, which is a Rainbow Quadrupedal 3. Now, I'm ready to present my research strategy. I inspired how human is good at guiding, no matter physical shape or size. We can find a common sense with different types. For example, people don't try to control learners' posture by applying forces in each joint. Instead, we focus on accomplishing the tasks, and we are controlling in the task space. From what I learned with these observations, I can tell that if someone wants to teleoperate the robot system, it's better to control it in a task space, and in a lower level, it's better to generate a torque control with a force control, because force control generates natural motions. But how can I make a system to collaborate with a human user and the robot? Since the robot is far away, it needs to be remotely teleoperated. In Team Nimbro, which attended in the ANA Avatar X Prize competition, they built 2 similar robots, and they are interacting with a robot, with a user, and they replicate its motions in the remote side. But that task would be very cumbersome and hard, since that robot is heavy and hard to move and very expensive. But virtual robots, digital twin, I would say, is free, and it doesn't have that cons. Here is a big picture of the system which I developed. On the far right side are the robot hardware, which I want to teleoperate and get feedback information from. Inside these blocks, low-level hardware communication and control software is placed. Most of the time, people refer to this side of the system as a backend. In the middle is a frontend of the system, which is a graphical user interface application built with Unity. It has many components, which are all important for intuitively visualizing, controlling the remote robot. The digital twin of the real robot is the main part of the application. It provides rich information to the user to be aware of the robot's real-time state. This kind of system is used in some recent research, but what is novel in this system is that digital twin has an interactable component, which is a red box. This box could be any shape. For instance, it could be a shadow of the virtual end effector. But I made this box intentionally red to make it obvious and intuitive for the user. User can interact with this box by using joysticks. For instance, user can grab it and float in 3D virtual space for changing the robot's reference pose, which is sent directly to the robot with high-speed communication. On top of it, it has many extra features. For example, user can press the analog trigger button for wearing robot's grippers, for picking and placing an object and interacting with a real environment. In the end of the day, all we want is to provide an immersive experience for the user to get the most out of the robot without making it too cumbersome and uncomfortable for the user. Now, I will present in more detail the graphical user interface application which I built by using Unity. This application is minimalistic and have only the most crucial components for intuitively visualize and command the robot. It has digital twin in the center, the virtual hands for intuitively grasping and interacting in virtual space. The red box, which is interactable, is for sending the commands to the real robot. Virtual display screens for watching outside environment through the cameras, which is attached to the remote robot.
이게 좀 설명을 해드리면 저 버추얼 핸드로 레드박스를 잡고 옮기면 실제
네.
로봇이 이제 저 레드박스의 그 오리엔테이션과 포지션을 추종하는 거예요. 레드박스로 하면은 이제 오리엔테이션 주기도 좀 보기가 편하잖아요. 그래서 저런 식으로 좀 구성이 많이.
So at the page 15,
Yes.
I'd like to have
Go back.
Yeah, one question. So the purpose of this page is to show us that your goal is to not controlling or manipulating the actual robot to teach them a lesson, some kind of thing, but using the virtual reality system to overcome the physical limitations or so. That was the
Yes.
point of this page, right?
This is
So-
to show where I get the inspiration.
Okay, so
And what is my
the reason why I'm
research
asking this
methods?
is it is a little bit so
Misleading.
in a nutshell, I can understand the intention of this page because yeah, so you're saying that this is about the research strategy and this is about the inspiration and there are only 4 things and I cannot get a clue about your intention. So what I'm understanding is that your goal is to make us understand first, humans are very good at guiding, therefore teaching a lesson directly by the touching or grasping the robot actuator may be a very good idea for let them learn how to do it. But the actual operation is very difficult time to time because if the robot is very heavy, it is very difficult to move it. So therefore your goal is to make a virtual reality system and teach them via the virtual reality system so that you can overcome the physical limitations. Is that correct?
Yes, sir.
Okay, I got it.
So general people can guide other people. For example, when they are teaching their learners, they can grab end effector of the learner and it can make it float to accomplish several tasks while doing it, task is accomplished and learner is learning. But I replace this learner with a robot because the robot cannot perform it by itself and it needs to be guided. I'm building this system to be used by the general people, not professionals. So it needs to be common sense and easy for them to understand and to get it keep going without getting a lot of training as other control stations. For this reason, I get inspiration and made it as similar as possible to this system.
Make it fun.
Thank you. Now I can present the motion control algorithm, which is implemented in my manipulator. My main reason for implementing the torque control motion algorithm is for compliancy and safety. This algorithm has three main components. Task space P, controller, which is simply a virtual spring between reference and actual end effector pose, which is illustrated in this right side picture.
Compliance control.
Yes. In order to improve stability and accuracy, Coriolis and gravity compensation component is necessary, which compensate robot's arm weight and nonlinear effects. Last but not least, joint space D, which is simply a damping, for each joint, is necessary for creating a smooth robot movements.
이게 좀 설명하면은 이게 거의 직구동이다 보니까 댐핑이 별로 없어요. 마찰이 반면에 그러다 보니까 일부러 마찰이 더 줬어요. 이 마찰이 너무 없다 보니까 관절마다 마찰을 추가적으로 줬고 그래서 오실레이션을 좀 줄이려고 했고 아까 저 태스크 스페이스 위로 올라가면은 버추얼 스프링이 있어서 목적지와 현재 위치 사이에 버추얼 스프링이 있어서 걔가 이제 훅스로우에 의해서 당기는 것처럼 이렇게 제어를 한 거죠. 저 그 버추얼 스프링에 의한 스프링 폴스를 구현하기 위한 토크를 이제 관절에서 생성시켜 준 거거든요. 그런 방식으로 한 겁니다.
So I have two poses, which is an actual pose, of the end effector, and I have a reference pose, which is coming directly from virtual reality headset by the red box.
레드 박스.
Yeah, and now I have to combine it together to create a virtual spring force. Simply, I can calculate it by subtracting poses and position of the actual end effector and the target, and multiplying it with gain P. But only position is not enough because end effector should follow the orientation of the red box as well. In order to calculate and make it follow for the orientation control as well, I needed to calculate the subtract cross product vectors of rotational matrix of actual and the target end effector.
저게 좀 설명을 드리면 그 액추얼 현재 로테이션 매트릭스랑 내가 원하는 타겟 로테이션 매트릭스가 서로 일치하게 되면 외적했을 때 다 0이 나오거든요. 90도 틀어졌을 때 그게 가장 큰 값을 보이거든요. 그래서 왜 그 두 가지 행렬을 이제 크로스 프로덕트 하면 내가 원하는 방향을 나타내기 위한 그 힘을 계산할 수가 있고 거기에다 개인을 곱해가지고 F하려고 했는데 사실 저게 모멘트거든요. 원래 저 라지 F가 지금 그러면 조금 헷갈려서 적었는데 저게 이제 렌즈예요. 폴스 3개랑 모멘트 3개거든요. 근데 모멘트 3개가 아래서 나오고 폴스 3개가 위에 이제 위치 오차로부터 나오는 거거든요. 그렇게 해가지고 자코비안 트랜스포즈를 거치면 조인트 토크로 랩핑이 돼요. 그런 식으로 되어 있는 거예요.
And should I understand that the F3S on the figure is same as that F, which is the range of the system?
Yes. This F is a virtual spring force,
Right.
which is a F, and it's a vector of 6-dimensional.
Right.
and the first three-dimensional is FL, and last third dimension is a FR. So
Yeah, so-
FR is a rotational, and FL is a positional.
So what I want to mention is that there is a mismatch between the symbols,
Yeah.
FVS and F. So
Yes.
Right.
it's a little bit hard for me to understand. But
Yeah.
there-
FVS.
Yeah, in the diagram it is a virtual spring, of course, but you should have, if you choose to use that term, then you should have to use that term with the F.
Yes, sir.
And in addition, KW should be included somewhere in the block diagram. Yes.
Oh,
You only put KP in the block diagram.
yes.
So
Right.
you may use another variable,
Yes, sir.
which contains all of these KW and KP.
Yes, sir.
And that must be a diagonal of the KP and KW, right? So
Yes.
KP, KW, 0, 0.
Yes.
That must be the KP in the diagram, right?
Yes, sir. And what is good about this mechanism is I can tune each variable differently for x and y z directions. And last but not least, I use the rotational matrix and quaternion instead of the Euler angles because I want to avoid gimbal lock problem. After calculating necessary task space virtual spring force, it needs to be translated from task space to joint space. Manipulator Jacobian transpose rescue. After deriving 6x6 Jacobian matrix and taking transpose, task space virtual spring force can be multiplied, so we can get 6-dimensional joint torque vector. For computer, it's easy and fast to calculate, which is the most important for controlling the robot with high frequency torque control. Nonlinear effects compensation is necessary for improving accuracy with lower gains. End effector pose error without compromising compliance. I utilized rigid body dynamics library, which is fast and accurate calculation method for easily getting nonlinear effect torque for each joint. Joint space viscous damping torque is simply a joint velocity vector multiplied with KD gain vector. One important advantage of utilizing joint space damping instead of the task space damping is that it enables tuning individually gain values for each joint. This is especially important for generating smooth motions for my manipulator, which has different types of actuators for each shoulder and wrist joints.
이게 좀 얘기를 설명을 제가 좀 드리면 원래는 그룹은 뒤로 좀 프리비어스 슬라이드 좀 더 가면
네.
더
네.
그 전 이게 원래는 그 레이저 포인트 한번 줘보세요. 이게 여기에다가 댐퍼를 붙였어야 되는 거거든요. 버추얼 댐퍼를 원래 여기다 버추얼 댐퍼 붙이고 버추얼 스프링 붙여서 여기서 힘을 생성시켜주거든요. 여기 착 달라붙거든요. 다시. 근데 여기다가 이제 버추얼 댐퍼를 빼고 각 관절마다 붙인 이유가 관절마다 사실 이제 그 마찰이 좀 달라가지고 사실 여기 이상적으로는 관절마다 마찰이 전혀 없다고 보면 여기다가 버추얼 댐퍼를 붙이면 그게 각 관절마다 그 댐핑 토크가 잘 분산이 되거든요. 관절마다 어디는 마찰이 크고 어디는 작고 막 그래가지고 여기다 버추얼 원래 댐퍼가 있는 거 없애버리고 각 관절마다 하나씩 튜닝을 한 거예요. 왜냐면 여기 손목 관절은 지금 기어비가 막 200대 1 그래가지고 높거든요. 여기는 그렇게 6대 어디는 9대 1 막 그러거든요. 그러니까 이거를 이제 구조관이 잘 튜닝을 하나씩 한 거예요. 근데 이상적이라고 하면 여기에다가 사실 태스크 스페이스, 이 카테시안 스페이스에서 댐퍼 하나 붙이면 이 관절 조인트 댐핑으로 다 매핑되는 거예요. 그걸 없애버리고
자코비안 트랜스포즈
네,
할 때는
요구하면
토크가
바로
그대로
되는데.
토크가 나올 텐데 근데는 우리가 감속비가 다 달라가지고 조인트 관절마다 튜닝을 했었어야 되는 필요성이 있었습니다.
But yeah, so I completely understand of your approach, but the question I want to ask is that if you, the methodology or the approach that you are using, which is the tuning all the B1, B2, B3, B4 parameters. So in that case, if the end effector lifts some kind of object, for example, or changes its load, for example, then the dynamic characteristics of each motor must be different. What I mean is that for example, if the motor 2, which is for Q2 and the B2, if they are moving in 1 radian per second, for example, they are showing some kind of performance. But if they're changing the frequency range to 5 radian per second, then the B2 will give us a different characteristics in this case. So what I mean is that if you select a B1, B2, B3, B4 as a function of the frequencies, then you can tune all the frequency ranges to match all the dynamics. What I mean is that if you move your system very slowly, then you might be able to achieve your goal trajectory of the end effector. But if you just increase your speed, for example, then those B1, B2, B3, which is tuned separately, will give you a different response to the motor set. Therefore, the entire trajectory can be corrupted, and that is
it would be case if I was controlling the manipulator's end effector in this position method.
Mhm.
I'm controlling manipulator as a compliant task space P control. In the
Yeah.
task space P control, since I'm generating these torque values from virtual spring,
So
it doesn't really affect the performance of the damping.
Really?
근데 비슷한 맞는 얘기를 한 거예요, 사실은. 이게 그 저게를 매뉴얼리 튜닝하게 되면 나중에 오브젝트의 무게가 뭐 늘어난다든지 뭐 그러면은 사실은 이제 퍼포먼스 떨어질 수도 있고 오브젝트를 뭘 들었을 때 좀 댐핑 그 토크가 생각보다 적을 수도 있고 하고 모션을 빨리 하거나 느리게 했을 때도 그 이너셔에 의해서 발생하는 이 토크를 충분히 못 잡아줄 수 있고, 그러니까 그런 얘기를 지금 하고 있는 거거든요.
네, 그건 하려면 교수님의 의견은 이제 어떻게 하면 좋을까?
예, 그래서 한번 해볼게요. 그래서 이제 질문은 뭐였냐면은
네.
저렇게 B1, B2, B3, B4, B5 다 개별적으로 튜닝하는 거 completely make sense 한데
네.
저게 B1이 constant일 거 아니에요. 어떤
네,
그냥
constant입니다.
rational number일 거 아니에요.
네, 그렇습니다.
그러면은 트랜스퍼 펑션으로 만약에 모터 인풋 아웃풋을 트랜스퍼 펑션으로 바꾼다면은
네.
B가 어쨌든 어디 트랜스퍼 펑션의 텀으로 들어가 있을 거고
네.
그럼 프리퀀시에 따라서 캐릭터리스틱이 달라질 거잖아요.
네, 그렇습니다.
그러면은 slowly moving 할 때 인풋 아웃풋이 트랜스퍼 펑션이 거의 1과 같을 텐데 fastly moving 하면은 트랜스퍼 펑션의 페이즈라든지 이제 이런 매그니튜드가 막 달라지기 시작할 거고
네.
그게 모든 B1, B2, B3, B4, B5가 아주 좋은 퍼포먼스를 보여주지 않으면 예를 들면 이렇게 콜라보레이션을 해야 되는데 얘가 갑자기 빨라져서 뭐 이런 식으로 움직인다든지 하는
정확히 완전히 이거 되게 잘 얘기. 이게 사실 이승기 교수님 이게 사실 다 그룹안 말고 그 다음 이어받은 애 그거 해야 돼요. 왜냐면 저희 실험할 때 그렇거든요.
네.
지금 너무 빨리 움직이거나 뭐 매스 무거운 거 하면은 얘
소리가
못 따라
이상해져요.
이상해져요. 그래서 저거가 공부해야 되는 거고 리서치 해야 되는 거거든요. 그룹안은 지금 튜닝을 해놨지만 컨스탄트하게 저거를 나중에는 저걸 약간 어댑티브하게 만들어줘야 될 것 같아요. 그거 되게 좋은 일이에요.
네. 교수님의 의견은
그래서 지금 B1, B2,
적어놔야
B3,
돼요.
B4, B5가 세팅이
이거
되어
같은
있다면은
것들을
those are
코멘트 다 적어놔야 돼요.
those are specifically for specific end effector velocity conditions. Okay? So if you move 1 meter per second of your end effector, and if it works okay, then that means those are only for that 1 meter per second conditions. If you increase your velocity, for example, 5 meter per second, then your trajectory might be corrupted. That's my guess. So
yes.
yes, and in your turn that you are not controlling the position, but you're only using the task space control. But the task space is about the position, Cartesian position, right? So
Yes.
이게 진짜 좋은 얘기 하시는 게 만약에 무거운 걸 달거나 모션이 빨라지면 저 K 값을 이제 올려줘야 되거든요. 그에 맞게.
네.
이 K 값 올려주면 당연히 댐핑 코에피션트도 바꿔주고 같이 올려줘야 되는데 여기 정해버리면 이 K 값에다 이거 하면 알아서 딱 배분이 될 텐데 이거 하나씩 하면은 이거 맨날 튜닝하면 안 되는 거잖아요.
네.
그래서 그 문제가 확실히 있어요.
네,
그래서
맞습니다.
원래는 우리가 무거운 거 이거 높이 거 구르면 할 수 있잖아요, 이거는.
네.
그러니까 그런 걸 그렇게 나중에는 이제 그런
네,
메소드를 지금 개발적으로 한 걸 좀 바꿔줘야 돼.
네, 알겠습니다.
아주 좋은 얘기를 해주셨습니다.
네, 감사합니다.
사실 저도 그거 느끼고 있는 거라 그거를 딱 말씀해 주셔서 계속 진행을 해주세요.
네. After calculating these three different torque vectors, they all can be added in a vector. These vectors can be added together and sent directly to each joint to generate compliant, accurate, and smooth motions. However, it is not enough for manipulator, which interacts with outside environment and manipulating objects, which brings me to the next problem, which I solved with my own novel strategy. While carrying heavier objects, end effector doesn't follow reference pose accurately. This phenomena is the most relevant for up, aka Z direction. In order to reduce this pose error, we need to increase the virtual spring stiffness, aka test space Kp gain. But this method has its cons. Most importantly, whole manipulator becomes stiff and compliance fades away. Means the motion is not safe anymore. For this reason, I had to think differently. If I could determine object's weight, then I can update manipulator's model accordingly, so manipulator would act weightless. In order to calculate object's weight, I utilized one of the most fundamental laws of physics, aka Hooke's law and Newton's law. Hooke's law provides us a formula to calculate force, which is applied to carry the object by using spring constant and displacement. But we already calculated this force in three-dimensional space, which means I can get the force in the Z direction just by grabbing one variable from this six-dimensional vector. So next, by deriving Newton's first principles, I can calculate object's weight by dividing it by g, gravitational constant.
그래서 이게 약간 매뉴얼리한 건데 물건이 버튼을 누르면 오브젝트의 무게를 알 수 있어요. 처진량으로. 그러면 오브젝트 무게 300g이다. 아니면은 그 지금 그래비티 컴펜세이션에 300g 줄여주는 거예요. G를 업데이트 시켜주는 거죠. 근데 이렇게 했더니 좀 문제가 있는 게 저거 사실은 저도 아까 그거 KP 스프링 선수도 같이 높여줘야 될 것 같아요. 근데 이렇게 했더니 문제는 물체 핸들링 할 때 자꾸 흔들리고 막 그래가지고 생각보다 참 좋은 방법은 좀 아니긴 하더라고요. 그래서 한번 진행해볼래요?
네. Weight of the object is calculated in every loop of the motion control, but the model will be updated only when necessary, which is determined by the user when calibrate button of the joystick is pressed. Now I'm ready to present a hardware. My target is to develop a lightweight manipulator with back-drivable shoulder and compact wrist joints, and also soft gripper with different with a depth camera. My choice of actuators for shoulder joints are my actuator company's R&D X series actuators. For wrist joints and gripper are Robotics company's Dynamixel XM 430 series servo motor actuators. Whole manipulator hardware is only 2.21 kilograms, which is even less than target. It was a 3 kilograms total weight target. This manipulator has many advantages. I utilized RMD quasi-direct drive QDD actuators because it's inherently robust, no friction, back-drivable, zero backlash, and also torque controllable with high-frequency CAN bus communication. Minimalistic design, simple design makes it easy for maintaining, fixing, and rebuilding. Main reason for building these carbon tube links is for clean industrial premium look with easy cable management. overall manipulator structural strength is able to hold up to 20 kilograms. Being attached at the end of the manipulator, gripper has to be as lightweight as possible. By using simple, smart, and my novel design, now this gripper's overall weight is only 160 grams. 50% of this weight is belong to its actuator, which is inevitable. Simplistic design with fewer parts makes it easy for assembly, which is only a matter of few minutes. This blue part of the gripper is 3D printed with TPU material. For improving friction, I glued special black resin material inside grippers. By changing its shape, gripper can hold up to 80 grams, which is 5 times heavier than its own weight. Grippers can open from 0 to 85 millimeters in half a second and close as well. The most importantly, this flexible material makes this part of the manipulator highly resistant against collisions without damaging itself or the object which is collided with. I think this is the most crucial because we observed that people and children are most likely to hold or interact with the grippers by touching it directly. Gripper actuator is also controlled with a torque control, which makes it compliant and easily modifiable for handling different objects. But most importantly, it's also intuitive for the user to control just by varying the grip button state of the joystick. User can control it with a gripper state. I decided to utilize the latest and one of the most capable depth camera sensor in the market available while being the smaller and lightest. This camera is smaller than golf ball and can provide depth information as near as 7 centimeters, which makes it best solution for using with the manipulation tasks. Camera needs to be tilted down 25 degrees in order to provide clear view for grasping objects. Now I'm ready to present the system architecture. This system has many different components and built with different tools. For instance, graphical user interface application is built with Unity using C# programming language. Real and simulated robot side of the system is running in Ubuntu operating system and built mostly using C++ programming language for speed and performance. I also added ROS features for this software package in order to make it universal and easy to work on for my teammates and the other researchers. Different kind of communication protocols are utilized for each hardware component and all put together. Front end and back end is communicating through TCP/IP protocol. Now I'm ready to present my experiment setup. This is a simulated robot experiment setup. I built this bench for evaluating this system. In the first experiment, I put 3 dumbbells with different weights for evaluating weight estimation algorithm performance. In the second experiment, I put 5 square-shaped objects with holes inside for attaching and detaching from the peg. This is a real robot experiment setup. I built this test bench for evaluating real robot system. In the first experiment, I chose the wooden objects with different weights for evaluating system performance and feasibility. In the second setup, I put 5 square shapes objects, which is exactly the same as a virtual setup. Goal of this experiment is mainly testing human factors such as motion sickness, nausea, comfort level, confidence, and performing tasks. Secondly, measuring systems performance by measuring feasibility and time taken for accomplishing each task. Last but not least, algorithm stability, usability, and also accuracy. Here, I can present the results with this video demonstration. On the left top side is a screen capture of gazebo simulator and real-time graph which is showing estimated weight continuously. On left down side is a screen capture of the graphical user interface application captured from head-mounted display. Based on this experiment, I can claim that human factors are excellent, even after performing and using virtual reality headset for a long periods of experimental time. I have never experienced motion sickness or nausea. Overall system performance is good, and no limiting factors for this target application. Algorithm is stable and accurate.
이렇게 보면 이제 어지러운데
그건 지금 포렉스로 했었어가지고
아.
지금 발라줘가지고. 네.
Can I ask one question?
Yes, sir.
So comparing those two virtual experiments,
Yes.
you are adapting a gravity compensation law to the second simulation, right? Is that correct?
Oh, yes, sir.
So the simulation number 1, there's no gravity compensation. In simulation number 2, there's gravity compensation, right?
So here is a gravity compensation for manipulator itself.
I mean the external, the payload weight compensation.
Oh,
Was
so
it not applied in the simulation?
So in this experiment, I have 3 dumbbells,
Yeah,
which
and-
different weights,
Yeah.
and I want to estimate their weights.
Only the estimation, not the compensation?
I estimating, and if user wants to press a button, it's added
Okay,
and
but-
compensated.
But this simulation video is not for that, right?
And there is a compensation as well when I press a button.
Really?
Yeah.
The reason why I'm asking is that in the first experimental video, the relative distance from the the cube and the actual dumbbell, there's a different distance because of the virtual compliance control working
Yes.
on it. But if I'm understanding correctly, if the gravity compensation is rightly applied, then always the end effector and the red cube must match its vertical position because gravity has been compensated. But even in this case, there's a gap between the red cube and the actual the actuator. So
Okay, so I will start it again. It's the beginning of the video. In the beginning, I don't press a button.
okay,
I'm just estimating the weight.
okay.
It's 0.5 kilograms. And the weight of this dumbbell was a half of it, which is a 0.25 kilograms.
Okay.
And this one is 0.5 kilograms. You can see it's matching 0.5 kilograms. And in the last one, it's a 0.75 kilograms. And I'm estimating it's in the middle. It's pretty accurately. Now it means whenever I press a button, it's going to compensate it. And in the rest of the video, now I'm going to compensate it. Holding this object, now there is a difference. And when I press a button, it's going to be reduced eventually.
Hmm.
You can see from here.
Got it.
Now there is a almost, when it's stable and the reference pose is not moving,
Okay.
there is no difference
Okay.
in the Z direction.
Okay.
But when I put down the object, now there is a minus error
Okay.
because the model is updated accordingly with the added weight.
Okay.
And the manipulator, when the dropping the dumbbell, now manipulator is not following the end effect, reference end effector but it's flying because it's estimating, it's thinking that there is a weight. And when I press it again, it's updating again and it's coming back. As you can see over here.
Right. Right.
이게 완전 매뉴얼이에요. 누르면은 됐다가 또 누르면 그게 컴펜세이션, 그래비티 컴펜세이션 추가된 게 없어지고.
근데 사실은 제가 어제는 추가적으로 이제 엔더 팩터가 잡았을 때는 에스티메이트 하고 부턴 눌렸을 때는 업데이트 하잖아요.
네.
근데 넣고 나서는 하니까 많이 올라가더라고요.
네.
그러니까 놓았을 때는 로봇이 직접 제가 이제 오브젝트를 놓았다, 안 틀고 있다라고 알 수 있기 위해서 엔더 팩터의 그리퍼의 스테이트를 알면서 이제 열었다라고 하면은 그냥 그
Compensation.
컴pen세이션 없어지고 그냥 마니플레이터 사실 자기 웨이트를 컴pen세이션 하는 걸로 했습니다. 근데 이 비디오를 전 이틀 정도 지났어가지고.
계속 진행합시다.
In this video, I'm trying to perform.
빨리 진행해.
I need to perform these delicate tasks because it needs to be accurately put together, and the speed matters as well. I swapped these objects, put 5 of them all together in the pack, and take it out and put it again. Means I swapping 5 objects in less than 3 minutes. Algorithm is stable and accurate control. No motion sickness, nausea, and it's very comfortable while doing for the user. Now, here is the experiment setup from the real manipulator. Here's a real manipulator and here's the objects. I'm performing pick and place. Pick and place is also delicate tasks. It needs to be accurately orientation and position of the end effector should be controlled. While performing this, I had never experienced motion sickness or nausea. And performing this task, swapping 5 objects, it took me less than 3 minutes, which is very similar to Gazebo robot.
The reason for having no trouble of nausea might be because you're so adapted to the system. Maybe.
Now I have to test it with different kinds of people.
Okay.
So Manipulator's hardware is also robust and stable. We added active cooling for shoulder joints. That's why there is no heating effects as well. Camera sensor is very clear. Judging from this graphical user interface application screenshot, and stable, streaming all the time without any latency or lag. As a conclusion, all minimum requirements are accomplished in 1 year. VirtualBox and digital twin concept has been proved. Virtual application has been developed. Communication system with robot has been implemented. Robust and easy to maintain manipulator hardware system has been developed. Software system for controlling manipulator has been developed. Basic algorithms for compliantly control has been implemented. In the future, current method is working, but further control algorithm improvements are necessary. Next step is to control the manipulator together with the quadrupedal robot. Whole body motion control algorithm is necessary for this reason.
끝났네.
Introduction note 있습니다. 여기서 이번에는 해야 되는 것 태스크들이 pick and place랑 문을 열고 버튼을 누르는 거는 목표에다 써가지고 매니플레이터를 개발하고 쿼드루피드 로봇이랑 합쳤습니다. 이제 시스템이 다 작동하고 나중에는 더 발달하고 개발하면 될 거라고 생각합니다.
Okay. 질문 이것은
Thank you. And it was very interesting and with a very reaching of these movies in here. So I enjoyed for your presentation time. My recommendation is that why don't you include some numbers in the conclusion? That means you in your experiment and result you describe only some task-based one. So
Yes.
it opens door, it successfully this opens door, successfully this pick and place of some part. But it's not easy to understand the correct performance of this system. So why don't you evaluation? Why don't you evaluate your system in terms of something numbers? Like in your experiment, you describe about your system is stable and your system enables the accurate weight estimation. However, why don't you something include some numbers on it? How much is accurate? How much is stable? So I'm not sure that is the uncommon things in some robotic system, but
Yes, sir.
in my impression is that the conclusion it embraces only something, some phenomena or something, the task-based one.
Yes, sir.
So that is my recommendation.
Yes, sir. Thank you.
이승기 교수님.
Yeah. Okay. So I have one question, two comments. Question number one is that why do you use compliance control for controlling the system? So this is for the people who doesn't understand the first of all basic robotics. So for example, if you just move your Oculus joystick,
Yes, sir.
then if you just can estimate your current pose of the joystick, then you can just directly apply that position into your robotic manipulator. Is there a reason for this compliance control? Because in the most cases, compliance control is for human-robot interaction. For example, if you push your end effector, then the goal is to make the robot being pushed away so that they can handle it more safely like that. But I can see not those kind of scenarios in your videos or materials.
So I wanted to control it compliantly because by doing so, it's safer for deploying outside. We went to the expo in the Incheon and we attended for the exhibition there, and the people were all around, and sometimes they are touching, and when it's touching, if the
Okay, I get the point.
if it's a compliant, and the user is not able to see whether the robot is colliding with something or not, because the camera is only attached to the end effector, and the perspective, the field of view is very limited.
So what I'm
In that
asking is that
cases,
during the experiment or your scenario cases that you have demonstrated,
Yes.
I believe there's nothing that covers that kind of human-robot interaction. So I'm not sure. And of course,
Yes.
the problem with the compliance control is that the accuracy of the end effector pose might be corrupted because of the unsatisfactory gravity compensation might result in the deformation of the differential string. That means your reference prediction might not be satisfied by your end effector. So there
Yes.
might be.
That's why I was comparing my system with the industrial robot. Industrial robots need to be very accurate because
So your goal is
they are performing these tasks autonomously. They have the loop closure and they have a feedback system. They can know whether the task is performed correct or not. But that kind of system is not implemented in my system. In my system, user is visualizing in real time. For example, let's say I want to open the door, and the door is a little bit more farther. I can bring it more farther. The red box can be altered, the position and orientation by the user. And when users was teleoperating this system, I observed that they are not really concerned about the accuracy of the end
Small
effector
feedback
because they are watching most of the time the display. If the display is showing the end effector and the object to grasp, if the object is a little bit farther and the end effector is not accurately grabbing it, then they can go a little bit farther, and so the end effector is going to follow it.
So what are you saying is that you, as an operator, you can adjust to these kind of bubble?
Yes, sir.
Okay.
For that reason, since there is a human in loop system, this system, the most priority was making it comfortable for the user.
Okay, got it. So I'm satisfied with that. And about page 23. Yeah, you can just press 23 and enter. Yeah, thank you. And actually, yeah, there's one comment. So your model update is only applied to the C and G matrix update.
No,
right?
no, only G matrix.
Okay, G for gravity compensation. But as the professor also mentioned that in this case the KD gain or
Yes.
the controller gain or KD gain must be increased for matching in order to maintain the performance.
Yes.
So the reason for that is because by grasping that mass, external mass, your moment of inertia also has to change.
Yes, sir.
So that means this is some kind of suggestion for the future research
Yes,
that
sir.
you might be needed to use some kind of model-based control theory, because the KP or the KD is actually some kind of extension of the PID controller,
Yes,
which is
sir.
a very model-free controller. So
Yes, sir.
so you cannot do some kind of validation of the performance in the PID control base. So what I'm suggesting is that first you need to update a mass for gravity compensation for the static position, but in order to make a satisfactory dynamic conditions, you may need to update the moment of inertia of the entire system and use the model-based system. So, for example, how can I put this? LQR, I don't know, or if you want the robustness, you can use a sliding mode control like that. So,
Yes, sir.
yeah, that might be your future research. That's my
Thank you.
question. And yeah, last question. In the actual experiment, why didn't you test your weight compensation?
Oh,
Was a pinpoint? So in the simulation, you demonstrated about the weight compensation, but the actual experiment, you just only
그게-
picked 10 places.
그게 했더니 아까 그 문제 때문에 흔들림이 좀 심했어요.
There was a vibration?
네. 그래서 이거를 해야 되겠다는 생각이 지금 되게 좋은 얘기 하셔가지고 딱 예측한 대로 이게 뭘 들었더니 S가 높아진 거잖아요. 이너샤랑. 그러다 보니까 개인이 안 맞아요. 그러니까 이거 들면 이렇게 가는 거예요. 여기 그 댐핑도 안 맞고 그래서 가벼운 거 아까 블럭 할 때는 괜찮았는데 이런 거 들으면 그런 거예요.
accurately
여기 흔들리는 거 보시죠? 조금씩.
estimating 하긴 하지만 물건을 이제 움직였을 때
원래 이게 뺐어요.
Gmatrix만 compensation 해가지고
흔들리잖아요. 뭐 털털털. 이거 들 때 더 그런 것 같은데.
And maybe the main reason for this oscillatory motion is because your compliance controller does not have a damper in the end effector.
yes, it doesn't have end effector
Right.
damping.
Yeah, so that might be the one reason for the vertical oscillation because
뭐 흔들리죠.
yeah, the mostly
이제 compensating.
yeah, the mostly your desired position is located here, but the gravity is making your end effector moving a little bit lower, and there might be a vertical oscillation.
이거 안 맞으면
I implemented in the first place when I was planning this motion control. I also put
되게 어렵다.
end effector velocity control as well. This is D gain for velocity compensation, task space damping. I
Controlling end
I-
effector velocity.
S에 꽤 많은
yes, end effectors positional velocities.
Also controlling the velocity. Is the velocity contained
No, no.
in your state?
No, no. So not only joint space D, I implemented task space D as well in the first place.
Okay.
But I removed it. I didn't put it in the block diagram. The
Right.
reason for that
붙였어요.
was robot was not
원래
stable at
저렇게 해야
all
돼가지고.
when I put it because it is stable in its narrow task space.
저희 내내
But
개발한 거도 한번 좀.
the robot is in a dynamic, and when it's stretching its hand, robot becomes very unstable.
Yeah, because the servo motor at the root might have a high amount of torque necessity, so
Yes.
yeah, the performance may be degraded. And
She's a
also there may be a
torque.
structural vibration happening, so
Yes. And the coupling effect is very strong as well because there is a pitch joint, 3 of them in a row, all together.
이거 보고서 이거 아마 정리를 해야 될 텐데
감사합니다.
제가 적어놨어요. 이승기 교수님 코멘트 댐핑 뭐 이거
네네.
속도나 이거 활용할 때 이거 어떻게 이거 PKPK 해가지고 사인을 해주시면
감사합니다.
예, 그 다음 심사가 있어가지고.
네, 알겠습니다.
아유, 수고 많으셨습니다.
아, 예, 고생하셨습니다.
이거 저희가 마무리
예, 예. 먼저 일하는 감사합니다. Anyways, great job. anyway.
이게 좀 다 해도 돼요.
예. Thank you.
가수를 해주셨는데 네, 불반 졸업해야 돼요.
감사합니다.
이쪽에서 그냥